Estimation of acids in acid mixture conductometrically. In this experiment, you have to estimate amount of strong acid and weak acid present in the given acid mixture. The strong acid is hydrochloric acid and weak acid is acetic acid. You know that the resistance of any object is directly proportional to its length and inversely proportional to its area of cross section, or R equal to rho into L by A. The constant proportionality rho is called resistivity or specific resistance. The inverse of resistance is known as conductance, that is C equal to 1 by R. By substituting the values of R, we get 1 by rho into A by L. The 1 by rho, the inverse of resistivity, is known as conductivity or specific conductance kappa into A by L, or conductivity equal to C into L by A. Means the conductivity is equal to conductance of material of length L centimeter and area of cross section is A square centimeter. Let us take an example of water. The conductivity of water is very low since it contains very few number of H plus and OH minus ions. If electrolytes are dissolved in water, the conductivity of water increases because electrolyte furnishes their ions. The conductance of electricity by ions present in the solutions is known as electrolytic conductance or ionic conductance. So this electrolytic conductance depends on nature of electrolytes added, size of the ions produced and their solvation, nature of solvent and its viscosity, and concentration of electrolyte. How to measure the electrolytic conductance? If you measure the resistance, we can convert into conductance because inverse of resistance is known as conductance. The resistance is normally measured with the help of Wheatstone bridge, but we will face two problems for an ionic solution using Wheatstone bridge. The first problem is passing direct current, which changes composition of the solution. The second problem is it is not possible to connect the solution directly to the bridge. The first problem is resolved by using alternating current. The second problem is solved by using the specially designed cell called as conductivity cell. This is the conductivity cell. This conductivity cell consists of two platinum electrodes coated with platinum black, separated by desired distance and unit area of cross section. The solution between these two plates is measured as specific conductance, but absorbed conductance is not equal to specific conductance because these two plates are not exactly 1 centimeter apart and area of cross section is also not equal to 1 square centimeter. The quantity L by A is called as cell constant. Normally cell constant can be determined by measuring the resistance of the cell containing solution whose conductivity is already known. Once the cell constant is determined, we can measure the conductivity of any solution. We will provide acid mixture in 100 ml beaker. First, wash the conductivity cell with distilled water and immerse cell in this acid mixture. Put this magnetic paddle to mix the solution. Fill the burette with sodium hydroxide solution. Then switch on the instruments and measure the conductivity of the solution. Before addition of any amount of sodium hydroxide, note on the conductivity of the solution. It is 26.3. In each step, we have to add an increment of 0.5 ml of sodium hydroxide till you get initial conductivity or around this value. At 0.5, conductivity is 20.8 or 7. At 1, conductivity is 15.6. At 1.5, conductivity is 10.7. At 2, conductivity is 8.6. At 2.5, conductivity is 9.7 or 8. At 3, conductivity is 10.7. At 3.5, conductivity is 11.7, 11.8. At 4, conductivity is 14.2. At 4.5, conductivity is 17.2 or 3. At 5, conductivity is 20.3. At 5.5, the conductivity is 23.2. At 6, conductivity is 26.0 or 1. Now stop the titration. Switch off the instruments. Wash the cell and keep the cell in distilled water. Using this data, you have to find the equivalence points. Plot a graph of conductivity versus volume of sodium hydroxide. For 0, the conductivity is 26.3. Put a cross mark and circle it. For 0.5, conductivity is 20.8. At 1 ml, the conductivity is 15.6. At 1.5, the conductivity is 10.7. At 2 ml, the conductivity is 8.6. At 2.5, it is 9.7. At 3, it is 10.7. At 3.5, it is 11.7. At 4, it is 14.2. At 4.5, it is 17.2. At 5, it is 20.3. At 5.5, it is 23.2. At 6, conductivity is 26. Now, connect these points by drawing a straight line. So these points, one more straight line, and these points connected by drawing a third straight line. The volume corresponding to the intersection of the first and second straight lines is taken as V1. The volume corresponding to the intersection of second and third straight lines is taken as V2. For 0, the conductivity of the solution is 26.3 is due to the presence of highly mobile H plus ion of strong acid, that is HCl. On addition of NaOH solution, the conductivity of the solution decreases rapidly due to the replacement of highly mobile H plus ion of HCl by less mobile Na plus ions of sodium hydroxide. At this point, all H plus ions of strong acid is replaced by Na plus ions of sodium hydroxide. There is no ion to replace. At this point, the acetic acid dissociates. The dissociation of weak acid was suppressed by strong acid HCl. Once the strong acid is neutralized, the acetic acid dissociates. So H plus ions of that acetic acid is replaced by Na plus ions of sodium hydroxide, forming sodium acetate, that is responsible for slight increase in conductance. After the replacement of all the H plus ions of weak acid, there is no ion to replace. The OH concentration increases, that is responsible for steep increase in conductance. This rapid decrease in conductance is due to the replacement of highly mobile H plus ion by less mobile Na plus ions. The slight increase in conductance is due to the presence of formation of sodium acetate. Steep increase in conductance is due to increase in concentration of OH minus ion. The V1 volume indicates the amount of sodium hydroxide required to neutralize strong acid, that is HCl. V2 minus V1 gives the amount of sodium hydroxide required to neutralize acetic acid. Using this, you have to calculate the strength of hydrochloric acid and acetic acid, then amount of these acids in acid mixture.